Welcome to Calculus. Today we will investigate writing and graphing a function and its derivative function, focusing on using algebraic strategies with the limit of the difference quotient and graphical comparison of features of a function and its derivative. Let's take a look at three examples. The first will be linear, the second will be a cubic function, and the third will be a radical square root function. Our first example here is a linear function, f of x equals 1/3 x plus 1. So looking at the instructions, we want to start by differentiating that function. Once we do that, we're going to graph both the original and its derivative on the same coordinate plane. In this case, not by creating a table of coordinate points, but from the slope-intercept form. So let's begin by differentiating, and the way we'll approach this is by using the definition of the derivative. And recall how we had seen that in previous work in this unit. The definition of the derivative is f prime of x equals the limit as h approaches 0 of really what is equivalent to slope, f of x plus h minus f of x. That would be our rise, all over simply h, which is the run, the distance between our x and a second point on the curve. So that's the definition that we'll use to differentiate here. So we'll fill it in specifically with what we've got here on the left. So we see f of x itself is 1/3 x plus 1. We'll go ahead and define f at x plus h to help us with the simplifying. So recall, it's a composition. Wherever I see x in the original, I'm going to write instead x plus h. And that allows me to fill in this difference quotient. So let's do so. So our derivative, f prime of x, equals the limit as h approaches 0. Remember, that's really creating a tangent line. When we're doing a derivative, we're looking for the slope of the tangent line, which is equivalent to the slope of the function at that point. F at x plus h will write here in the red, that's 1/3 times x plus h plus 1, and I'm going to place that whole expression in brackets, minus, and this is f of x, 1/3 x plus 1, and that is all over h. So as always, where we start simplifying in the difference quotient is in the numerator. So my next step will look like the limit as h approaches 0. And I'm going to let the parentheses or the brackets go on that first red expression, the f of x plus h, and then distribute through the third. So that will give us 1/3 times x plus 1/3 times h plus 1. And then one thing we always have to be mindful of with this minus sign is that it will distribute to all the terms in f of x. So as I let the parentheses go, it becomes minus 1/3 x minus 1. It's easy to miss that minus sign on the 1. And still over h. At this point, it's good to see what will cancel. So I see 1/3 x here and a minus 1/3 x. Those will cancel with each other. I also see plus 1, minus 1. I use those opposite slants to indicate what's canceling what, because that can be a challenge to keep it all organized in the numerator. That is reduced down a lot. That's now the limit as h approaches 0. The only thing left in the numerator is 1/3 times h divided by h, and that introduces yet another cancellation. H divided by h is 1. And we're really ready to find the limit as h approaches 0 now. If you can get rid of that h in the denominator, it circumvents the indeterminate 0 over 0. So all we're left with is the limit as h approaches 0 of 1/3. So recall when we're taking the limit of a constant number, there's no substitution to make. That equals 1/3. Now we're treating that as a function. So this is f prime of x, the derivative of f of x equals 1/3. And at this point, we're ready to graph our two functions. So we want to graph the original and we want to graph the derivative here on the same plane. So let's pick up, we'll graph the original in red. I'll circle it so that we identify it by color. That +1, that's my y-intercept. So I'm going to start there on the y-axis. And then I'll use the slope, 1 over 3, from this slope-intercept form to graph a second point. So I'm going to rise 1 and then run 3. And get rid of that counting now that we've placed our second point. And recall with a linear function like that, you can continue that pattern, rise 1 over 3, and you can even reverse it, down 1, left 3. And that gives us a way to graph this entire f of x quickly. And I'm going to label that f of x. Then I want to graph the derivative, which is here in the navy blue. So it passes through the y-axis at 1/3, and in fact passes through every x value at 1/3. It's a constant flat line. Once I graph that, I'm going to label it f prime of x. And that completes our first example. One thing we can notice here is that the derivative of a linear function that has a non-zero slope is a line that does have a 0 slope. Let's take a look at a polynomial function. So here's a cubic function, f of x equals x cubed minus 8x. And our task is really the same. We want to come up with the derivative of this function. So again, I'm going to use the f prime of x definition, which is the limit as h approaches 0 of that same difference quotient. So f of x plus h minus f of x, all divided by h. So just like in our first example, I do have f of x given already. What I need to record is what's f of x plus h. That's a lot of simplifying. Best to do it here before we place it in the difference quotient. So as I make the composition, it's x plus h cubed minus 8 times x plus h. And I'm going to work to the right here, and then we'll create our difference quotient below. So first thing is I'm going to take 2 of these x plus h's and multiply them. So what that's going to give me is x squared plus 2hx plus h squared. Now there is a third x plus h that I haven't distributed through, so I'll write that there. But I've distributed or done a double distribution with 2 of those. The third is left. And then I'll distribute the minus 8 through its binomial x plus h. So that's minus 8x minus 8h. At this time, I want to make sure to finish this distribution with that first product of the trinomial and the binomial. So I'm going to distribute the x first. It'll multiply times each of these 3 terms. So what we'll have is x cubed plus 2hx squared plus h squared x And then I also need to distribute, once I've finished with the x, this h through to each of those terms as well. There will be some common terms, so I'm going to stack them vertically so I can combine them conveniently. So h times x squared is plus 1hx squared. Those are like terms that will combine. H times 2hx is plus 2h squared x. And lastly, h times h squared is positive h cubed. I'll import the minus 8x minus 8h. And we can finalize this expression. So you can see just writing out f at x plus h here requires some algebraic simplifying. Reduces down to x cubed plus that sum 2hx squared plus 1hx squared is 3hx squared plus 3h squared x plus h cubed minus 8x minus 8h. So that is my f at x plus h. So I'm ready to create my difference quotient here. So I'm going to set it up. F prime of x, the derivative of f at x, is the limit as h approaches 0 of this green expression, x cubed plus 3hx squared plus 3h squared x plus h cubed minus 8x minus 8h. And that is subtracting the original, which is a lot simpler, x cubed minus 8x. And that is all over h. So before we head to our next step, what I want to do is deal with the parentheses. So there's no need to keep this parentheses around the green expression. There's no coefficient there. I do want to distribute this negative to the x cubed and the minus 8x in red. So it'll keep that x cubed negative. It'll make the 8x positive. And that lets me also drop the parentheses. Once I do that, I can see a couple cancellations at first. I see I've got x cubed that's positive and minus x cubed that's negative. Those will cancel. I've also got minus 8x and plus 8x. So that reduces down my expression to terms that have, each one has an h in it. So my next limit expression is limit as h approaches 0 of 3hx squared plus 3h squared x plus h cubed minus 8h. And that's all over h. So since each term in the numerator has an h factor in it, I can cancel one of them for each term. So 1h cancels, the square would cancel, that cube would turn to a square, and that h would cancel along with the 1 in the denominator. And what that gives me now is the limit as h approaches 0 of, on one level, 3x squared plus 3hx plus h minus 8. And that is ready now for direct substitution. So when I look at the limit, it's about h approaching 0. So I won't substitute anything for x. I'm just going to leave x as is. But anytime I see h, I'm going to substitute in 0. So this is 3x squared plus 3 times the 0 where h was, x, plus 0 minus 8. And we can observe a couple cancellations there again. The terms with 0 are going to fade away. And what we're left with is this derivative of f of x equal to 3x squared minus 8. And that we should box because that is our derivative. We've differentiated the x cubed minus 8x. Now what we'd like to do is graph those two functions on the same plane. So I'm going to zoom out so that we have some room to create a table. And what we'll do is let's make a table that has both the original f of x and its derivative. So I'll put my x values, and we'll choose -2, -1, 0, 1, and 2. So I'm leaving some room because I know there's some values there that I need to catch. F of x is x cubed minus 8x. And then the derivative, f prime of x, is 3x squared minus 8. So I want to create those tables, and the way I will do it is let's use the Desmos graphing calculator to come up with those y values. So we'll head to Desmos. And once we're there, I'm just going to input the two functions. So we'll call this f of x. That's the original x cubed minus 8x. Make sure I get the input correct. So there's our graph. It does head off the screen. So the way I'll treat that is I'm going to zoom out with the minus key. And definitely a classic cubic function there with the wave in the middle. I'm going to call f prime of x g of x just to keep Desmos happy, and that's 3x squared minus 8. And you can see that purple quadratic overlaid on top of the cubic function. So I want some table values so I can graph it on our notes page. And there I've got those, clearly an odd function because the output changes sign, but the numbers are the same. So -2 has an output of +8, +2 has an output of -8. -1 yields 7, 1 yields -7, and it does go through the origin. But I want to catch two other points here, and that's the max and the min of this function. So I'm going to just click there. I'm going to record in between -2, -1 on my table the x value -1.63, 8.71. And similarly, I want to catch the relative minimum down there in quadrant 4 at 1.63, -8.71. So I've recorded the 5 in the table and also those relative extrema. Now I want to get a table for this g of x, the one in the purple. So there's the points on that one, and it's definitely an even function. -2 yields 4, so does +2. -1 yields -5, 1 yields -5. The vertex is at 8. I'm sorry, 0, -8. But what I'm interested also on that purple function are the zeros. So the left one is at -1.63, which we got to notice is the same x value that gave a maximum for the green function. Similarly, on the right, the 0 on the purple derivative is 1.63. The minimum is also at 1.63 for the original. So we'll make more connections out of those. They're not coincidences, but kind of common features in the two graphs of the original and its derivative. But right now we just want a graph. So I've written those tables down, and I'm going to head back to the notes screen to finish graphing. So we can fill in our table now, and I'll put those two x values that we saw for the relative extrema / zeros, negative 1.63 and also 1.63. And let's record those values. So again, for this original, we had 8, 8.71, 7, 0, negative 7, negative 8.71, negative 8. We'll graph that one in a moment. Let's fill in for the derivative. That's 4, 0, negative 5, negative 8, negative 5, 0, 4. Very symmetric. In fact, both are very symmetric. Just one is odd. The other is an even function. Let's graph those. So the red function here at negative 2 has the value of 8. It does go slightly off my graph here. That's okay. So I'll just estimate this is about 8.71. At negative 1, it's got the value of 7. At 0, it's 0. Negative 1, negative 7. Negative 1.63, negative 8.71. Negative 2, negative 8. So that allows me to graph this cubic function. And there's our rough sketch of that original f of x. We can now sketch the derivative graph. So at negative 2, it has the value of 4. Crosses the x-axis where the original had its maximum. Negative 1 is negative 5. 0 is negative 8. And then we have very symmetric placement around it. On the right, it has its 0 where the original had its minimum, and then 2, 4. So at that point, we can graph the derivative. And that completes the task. Just to recap, we have found the derivative using the rule, the definition, which is this limit of the difference quotient. We then graphed both of these functions, the original and its derivative, using a table. Let's take a look at one last example that is a radical function, a square root. So our third example has the function f of x equals 5 times the square root of x minus 1. And let's give ourselves the full view there, 100%. So again, our task is to start by differentiating. So we'll jump right in. We know at this point we're looking at that definition, the f prime of x equals the limit as h approaches 0 of f at x plus h minus f of x all over h. So I see on the left f at x is 5 times the square root of x minus 1. That's the original function here. So our derivative is going to depend on f of x plus h. So we'll make that substitution here at the outset. So that's x plus h minus 1 under the radical. And I see that I really don't need the parentheses, so I'm going to eliminate them at the outset. Make sure that that is a clear plus. So we're ready to set up our difference quotient. F prime of x is the limit as h approaches 0 of this fraction. So the green one comes first. That's 5 times square root x plus h minus 1 minus the original f of x, which is 5 times the square root of x minus 1 all over h. So here we have to remember our strategies for finding limits when I have some square roots involved, either in the numerator or the denominator. And remember, the strategy is to multiply by the conjugate of the part of the fraction where I see the radicals. So where I'll go to create this is the numerator. I'm going to multiply both the numerator and the denominator by 5 times square root x plus h minus 1. And then what I'm changing to make the conjugate is minus into plus. That's the only operation I switch. And then I'm going to reproduce that conjugate in the denominator. Algebraically, that has the value of 1. Anything divided by itself equals 1. And that's what allows me to use that strategy. So I'm multiplying by the conjugate. And hopefully what that does is it'll cancel the h in the denominator so that I can avoid the indeterminate 0 over 0. Well, that gives us some algebra simplifying. So we need all the room we can find. Limit as h approaches 0 of a rather broad fraction. So we'll write it as a double distribution here. So what I'm distributing is the first terms, the outer terms, the inner terms, and the last terms. Now, the way we've created it, our first terms and our last terms are identical. So the way I'll record this first product is as 5 times the square root x plus h minus 1 squared. The outer terms are going to be a lot to write, but what we're going to see is we'll have an immediate cancellation. So minus 5 times x square root of x minus 1 times 5 square root x plus h plus minus 1. And then the last term, I'm sorry, the outer terms are going to be plus, trying to color code so you can track what's multiplying times what, times again 5 square root x minus 1. So what we see here, and we'll do the cancellation in a moment, but these terms are identical but opposite sign. So in fact, what I'll do just now is cancel them. And that'll take care of that kind of daunting algebraic expression there in the middle. And then the last terms, if I notice the one in the red and the light blue are identical. It is minus. So what I'll do is I'll write minus and then 5 times the square root of x minus 1 squared. That's still all over h. So that was kind of the largest expansion that we'll see on this one. So it's all going to shrink from here. The limit as h approaches 0. What I did neglect to write is the denominator, but that's okay because I'm not going to distribute this. What I want to leave there is that h. I want to leave it so that it's ready for cancellation whenever that becomes available. At this time, I'm going to simplify that numerator. So the simplification I'm looking at is this square. So it is going to square the 5. That'll become 25. but then the square root is going to cancel with the square. So that becomes x plus h minus 1 in parentheses. We've got a similar kind of squaring and cancellation of a square root over here in this red term at the end. That's going to be minus 5 squared is 25 there, and then x minus 1 when I let the square cancel with the square root. In the denominator, I've got h. One thing I noticed that I can do for simplifying there is factor out a 5. And that leaves parentheses square root x plus h minus 1 plus square root x minus 1. So now in my numerator, I want to distribute the 25. Well, what I'm noticing is I could wait on that. Let me get my parentheses back. Why I'm going to wait is because I see that I could cancel 5 out of both of those 25s with division from the denominator. So let's do that. Again, kind of reduces pieces before I distribute. So now I'll distribute these 5s through those numerator terms. So this is now the limit as h approaches 0 of, with the distribution 5x plus 5h minus 5. And then I need to be careful on the sign on this second distribution. It's negative 5 times x is minus 5x. Negative 5 times negative 1 is plus 5. All over h times square root of x plus h minus 1 plus square root x minus 1. You just keep chipping away until you get to where you can cancel that h down below. That creates some cancellations. So 5x minus 5x cancels, negative 5 plus 5 cancels. So in numerator, we have not much left. It's the limit as h approaches 0 of simply 5h over h times the square root x plus h minus 1 plus square root x minus 1. And that does the cancellation of h for us. H divided by h cancels. And what we've got left is something that we can now perform direct substitution with. So this is the limit as h approaches 0 of simply 5 in the numerator. And then in the denominator, I can let parentheses go, x plus h minus 1 plus x squared of x minus 1. So now there's only one occurrence of h left. So what I'll substitute there, direct substitution, is the value of 0. So this is 5 over the square root of x plus, instead of h, I'm going to put in 0, minus 1 plus square root x minus 1. These are now the same expression. Those are both square root of x minus 1 because that 0 is going to vanish. So my final form, and what I'll call this is f prime of x. The derivative of f of x is 5. There's 2 of them, so it's over 2 square root x minus 1. And that I will box. So that completes that first task. We've differentiated f of x using the definition of the derivative. Now we want to graph this function. So similar to what we did with our second example, I want to create a table and then go over to Desmos to generate the y values, and then we'll come back and graph both here on the same plane. Like we did, we'll give 3 columns so that we can compare our values of the original function and its derivative. One thing I am noticing is that this function, let me write it here, the original is 5 times the square root of x minus 1. So when I go to take my domain values for f of x, I know that under the radical, any negative result under the radical will be undefined. So I see that if I have 1 minus 1, that'll be 0. That's okay, but anything before that's undefined. So I do want to see an undefined term. So we'll start at 0 and then include 1, 2, 3, and 4. We can always add x values, but I think choosing those 5 x values will give us the most information for the number of domain values we've chosen. So f prime of x is what we just calculated. That's 5 over 2 times the square root of x minus 1. So let's head to Desmos and create those y values there. Desmos has the added bonus of letting you see the graphs before you have to graph them yourself. So f of x, the original is 5 square root x minus 1, so a very tall square root function there. And then g of x, which we'll just put in for our derivative, is the fraction 5 over 2 times the square root of x minus 1. And what I'll do is I'm going to drag this because clearly we have no values of either function in quadrants 2, 3, or 4. So really we just need to focus on quadrant 1. And let's get our table values. So we can see that original is a clear square root. The derivative is a rational function. But we saw that in the algebra. X landed in the denominator. So we'll create our table. And again, I don't want all those values. I don't want -1, -2, because that's extra undefined terms. But I do want to include 3 and 4. So those points show up, and that'll give us a good start to creating this square root curve. The 0 here is at x value of 1, so 1, 0. 2 is at 5, 3 is at 7.07, 4 is at 8.67. Let's also create for our g of x here. So I'll click that cog and then I'll select the table for the derivative. And it likewise doesn't really need those negative values. In fact, it doesn't begin until 2. It's got a vertical asymptote, it looks like at +1. So let's click and get some values for 3 and 4. So while the square root function rises as x increases, the derivative does the opposite. It decreases as x increases, but notice it's always above the x-axis. So we'll record those tables and let's head over and finalize our graph. We'll head back to the notes. So I just want to fill in what we saw here. So if at 0, both functions are undefined. We'll do the red one first. So 0 is undefined. 1 is at 0, 2 is at 5, 3 is at 7.07, 4 is at 8.66. The derivative's undefined for both 0 and 1. This one at undefined value at 1 is a vertical asymptote. At 2, it has the value of 2.5. At 3, it has the value of 1.77. And at 4, it has the value of 1.44. So now we're ready to graph. And we'll place this over here on the coordinate plane. So 0 is at positive 1. That's 0.10. 2, 5. 3, 7.07. And 4, 8.66. So off my curve, but that's, or off my graph, but we can sketch it in nonetheless. The derivative has a vertical asymptote at 1. And then its values pick up at 2. It has the value of 2.5. 3, it has the value of 1.77. At 4, it's at 1.44. And so we can sketch in that curve of the derivative. And that completes our third example there. Writing, again to recap, we wrote the derivative using the definition. Once we got that function, we used the calculator to help us generate a table of values. And then we graphed both the original and the derivative on the same coordinate plane. Thanks for joining for these 3 examples. I'll let you work on your problems now. I'll see you soon.